Knowledge representation. The process of structuring information in a way that AI can understand, so that it can make complex decisions and solve problems effectively, and structures it in a way that mirrors how humans think. Types of knowledge in AI. First, declarative knowledge. These are the types of knowledge that are facts of the world and are usually stored in databases, ontologies, and knowledge graphs. For example, Jakarta is the capital of Indonesia. 2. Procedural knowledge shows the method to do a task rather than just stating a fact. For example, knowledge on how to ride a motorcycle. Expert systems and robotics use these types of knowledge to do tasks that require sequences of actions. These types of knowledge is used in rule-based systems and machine learning models. Third, meta-knowledge. Knowledge of how information is structured, used, and validated. For example, an AI trying to determine if an information of how to drive safely comes from a reliable source like Wikipedia. 4. Heuristic knowledge. This knowledge comes from experience of the AI itself, such as trial and error, with the purpose of so that it can make educated guesses if there is no 100% right solution. For example, ChatGPT suggesting other methods to solve a mathematical equation. A search is one of the examples of algorithms that use heuristic knowledge. Fifth, common sense knowledge. Knowledge about basic principles such as water is wet, but AI has a hard time understanding them. So, to help it, AI is inputted by large databases with tons of information, so it can understand these kinds of concepts. Domain-specific knowledge. Knowledge that focuses on a specific field in the industry, for example, law, engineering, medical, business, and etc. The benefit of these kinds of knowledge is the information is very detailed. In return, the AI can produce very accurate results. For example, an AI that helps in gaming knows basic strategies, character skills, effective items or builds for a specific game. AI knowledge cycle. Knowledge acquisition. AI gathers data from various sources, for example, pictures, videos, articles, and etc. Knowledge representation. The knowledge gathered must be structured so that the AI can understand it. Knowledge processing and reasoning. AI applies logical inference, probabilistic models, and deep learning to process new knowledge, which enables AI to solve problems and adapt to various situations. Knowledge utilization. AI is used for real-world tasks such as automated virtual assistant, self-driving cars, and generate art on its own. Knowledge refinement and learning. AI always improves itself by over time by learning, updating, and getting smarter using new data and feedback. Logic-based representation. Proportional logic, representing knowledge using proportions and logical connectives. For example, P is it is snowing. It is not snowing can be represented as minus P, or in other words, not P. First order logic, introducing quantifiers, predicates, and variables to represent more complex relationships. For example, all cats are mammals can be represented like this. Semantic networks represent knowledge using nodes and links to show relationships between concepts. Nodes represent entities or concepts, and links represent the relationships between them. These are the nodes and these are the links. Frame. Frame A frame is a data structure that represents a stereotypical situation, object, or concept, and it contains slots for various properties and values associated with the object. Scripts, on the other hand, are sequences of frames that represent typical sequences of events or activities. This is the frame, and in the frame there's multiple scripts you can see here. Rule-based representation involves representing knowledge in the form of production rules to capture conditional relationships and actions. These rules typically take the form of if-then statements and are used to infer new knowledge based on existing knowledge. For example, a rule in a traffic setting: if the traffic is red, then your vehicle must stop. Ontologies. Ontologies are formal representations of a set of concepts within a domain, and the relationships between those concepts. They are used to define a common vocabulary for a particular area of interest and provide a structured hierarchical framework for organizing knowledge. Bayesian network, a method in which an AI tries to make smart guesses based on something that's uncertain. For example, these are dark clouds. The weather forecast says it might rain. You forgot your umbrella, so you're hoping it won't. This clue affects how likely it is to rain, but none of them is 100% certain. Bayesian network use just all the clues to calculate how likely is it to rain. How Bayesian network works. Nodes. It uses nodes to represent events or variables like rain, dark clouds, wet ground. Arrows are used to show how one event affects another. For example, rain. If it rains, then the ground is wet. Probabilities are numbers that are how likely something is to happen. Markov decision processes, a method in which AI tries to make smart decisions step by step, especially when each decision affects what happens next, and it finds the best path to reach its goal. Like if you're playing a video game and you're trying to win it, the four parts of an NDP. There are states, all the possible situations. For example, the robot is in the kitchen, living room, or hallway. Second, actions, the choices the AI can make. For example, move left, move right, pick up an object, and etc. Transition probabilities, the chance that one action leads to another state. For example, if the robot moves right, there's an 80% chance it reaches the next room, and 20% chance it bumps into the wall. Rewards, what the AI gets for doing something good or bad. For example, plus 10 points for finding a goal or reaching a room, and minus 5 points for hitting a wall. Real life examples. Medical diagnosis, using knowledge representation to capture symptoms, diseases, and medical expertise to assist in diagnosis. Example, if patient has a fever and a sore throat, then there's a possibility that he is enduring the disease called flu. Second, natural language understanding, representing linguistic knowledge to enable AI systems to understand and generate human language. For example, ChatGPT can understand a lot of languages. 3. Robotics, knowledge representation for spatial reasoning, object manipulation, and task planning in robotic systems. For example, robots can identify a pencil, pick it up, and write using it. Fourth, expert systems, representing domain-specific knowledge to provide expert-level advice or decision-making in various fields. Example, for bank-giving loans, if applicant's income is more than $50,000 and his or her credit score is more than 700, then approve loan. If applicant's income is less than $20,000 or has a bad credit, then deny loan. Planning and problem solving, Planning in AI refers to the process of determining a sequence of actions that will transform a given initial state into a desired goal state. It involves reasoning about actions, their effects, and the states of the world. Problem solving in AI involves finding solutions to complex, often abstract problems by using computational methods and algorithms. This can include searching for solutions, reasoning about possible actions, and evaluating potential outcomes. State space are all possible situations that you could be in while solving a problem. Example: in tic-tac-toe, every possible board position. Actions: the actions you take with the intention of reaching the goal state. Example: in tic-tac-toe, putting an X on one of the squares. Goal state: the condition where you want to achieve. Example: getting a bingo in tic-tac-toe. Search: moving through the state space until it achieves the goal state. For example, testing moves until you find a winning strategy. Uninformed search. Uninformed search algorithms, also known as blind search algorithms, operate without any knowledge about the goal state or the search space. They systematically explore the search space until the goal state is found. First one of the uninformed search, we have BFS, which is breadth first search. Explores level by level. If, for example, searching a maze by checking every path, that's one step too long, then two steps too long, then three, etc. BFS finds the shortest path with the fewest steps. BFS uses memory because it stores all nodes in the current level. The second type of uninformed search is DFS, depth first search. Depth first search explores as deep as possible down one path before backtracking. For example, in a maze, you keep walking straight until you hit a dead end, then back up. DFS uses less memory, or in other words, just one path at a time. DFS might not find the shortest path first, it could go down a long dead end. Uniform cost search. Uniform cost search expands the path with the lowest total cost so far, not just the shortest steps. For example, Google Maps prefers highways, low cost in time, over small streets which are high cost or demands a high amount of time, even if highways look longer. Pros: guarantees the least cost or time solution. Cons: can be slow if the time it takes to reach the goal state are long. Informed search. Informed search algorithms use more specific knowledge or heuristics with the intention the AI system achieves the goal state more efficiently. The hints are additional information to help the AI system go through more promising paths instead of wasting time in bad ones. First, one of informed search algorithms is greedy best first search. Explores the path that looks closest to the goal according to the heuristic or guess. For example, the exit for the maze is north, so keep moving north. Cons: not always optimal, can get tricked into dead ends. A search combines greedy and uniform cost search. The pros is this kind of algorithm is very efficient at finding them, but the cons are dependent and very dependent on good heuristic tip. Adversarial search. Algorithms are used when in game playing or decision-making scenarios where the agent is opposing an adversary. The algorithms usually find ways to counter the adversary's action while making the agent get the upper hand to achieve the goal. Example of adversarial search is minimax algorithm. It assumes your opponents plays the best moves. Then the algorithm chooses the moves that minimizes opponent's advantage and maximizes your own. Example, in tic-tac-toe, you block your opponent's winning moves while also setting up for your winning move. Second example is alpha-beta pruning. If you have a way that guaranteed a win, the algorithm won't bother to calculate the other ways and instantly executes the guaranteed one. For example, in chess, if one path has already given you a guaranteed win, you don't bother calculating other paths. The third example is hill climbing. Starts with a random solution and making small changes along the way so that it gets better and better. For example, trying different seating arrangements in class until noise level improves. Pros: it's simple and fast. Cons: get stuck on local peaks, which are good results but not the best. Simulated annealing. It's like hill climbing, but it tries out all the solutions with the risk of getting bad ones, with the intention to escape local peaks. Inspired by metal cooling, where when a metal is hot, its atoms move randomly a lot, but while cooling, it slows down, and the atoms eventually settle down and be in a more calmer state. Let's give you an example. At the cinema, you try out all of the seats, even getting the bad ones, until you find the perfect spot. Pros: it can accept local peaks, good but not the best. Cons: slower, depends on cooling schedule. What I mean by that is, at the beginning, it will have a lot of energy to check a lot of the solutions, but over time, its energy will deplete and it'll become more lazy and be more selective by keeping the better solutions.